Hello students, today we'll go for the next IR studies of phosphines, okay, and arsenic ligands, okay, of phosphine and arsine ligands, okay. So if you see that the ligands like phosphine, so we represent as PR3, okay, and arsine we represent ASR3. So where R stands for alkyl, aryl, halogens, etc. Okay, so this is what, and they form the complex with a variety of metals in various oxidation states. And the vibrational frequency spectroscopy is extensively used to know the determine the structure of these complexes. Okay, so if you see the vibrational frequency of the pyramidal structure of XY3 type ligands such as PH3, okay, and PF3, okay, and their halogenations analogues. The most simple phosphine ligand is the PH3 ligand, and the vibrational spectra of, if you see the vibrational spectra of NiPH3 nickel phosphine 4, okay, uh, then nickel NiPH3 carbonyl tries, okay, and NiPH3 PF3, okay, thrice. Okay, so this you can write like this is phosphine, okay, PH3, so yes, you can write PH3 capital here. So nickel tetraphosphine, and you can see tricarbonyl phosphine nickel, as well as phosphine PF3 phosphine trifluorophosphine 3, okay. If you see this complexes which was reported by the Bigon, okay, Gorgne Bigon, okay. So this was he studied on these complexes, and all these complexes exhibit see new the vibrations of phosphine pH at pH, exhibits pH, and bonding of pH3, okay. So this is what, and the vibration of NiP. So these three, okay, so he reported the vibrations of the phosphine pH3 NiP. So at 2370 to 2370 to 2300 1120 1120 to 1000, okay, and this nickel to this is 340 to 295 per centimeter, like this, okay. So this is how the Bigon has studied these complexes, and you can see the IR frequency, how it differs and how it helps for us for getting the different structural evidence from this, okay, IR spectroscopy. Even the trifluorophosphine, if you see the trifluorophosphine compound, that is PF3, okay, it also forms trifluorophosphine. It also forms the variety of complexes with transition metals, okay. So according to Ruck, so this is one scientist, KRUCK, okay, according to Ruck. So the frequency of PF phosphine of free uh, PF3, okay, of free PF3 trifluorophosphine free. So he observed that it is in the 892 to 860 per centimeter, 892 or 860 per centimeter, and these are slightly shifted to higher frequency to 960 to 850 per centimeter, okay. So this is going to higher, this is a free frequency of this free PF3 trifluorophosphine. It is going to shift to the higher level here upon complexation, okay. In some of the complexes like metal, okay, in some of the complex metal PF 3 4 times minus, okay. So this is PF3 4 times minus, this is complex, this is going to be observed here, the metal and this and this is how lower frequency is in some of the metals, and in some of the metals to lower frequency. So like in metals like M, okay, um, hydroium PF3 4 times, so hydride form. So you can see it is going to shift at lower frequency at 850 to 750, 850 to 750 per centimeter. So this is also at higher frequency also we have seen from this one, and if it's going to bind with the hydride type of this one, is going to form the lower frequency. So this is how the example of these phosphines the structural illustration is very much easy with the help of the frequency mode. So knowing the frequency mode of the complexes, okay. So this is how the IR spectroscopy is really helpful for the structural elucidation of the phosphine complexes. Okay, and even if you see the IR spectra of isotopic forms of trans, okay, nickel p triethyl phosphine x2, so transform, okay, where x may be chloride or bromide here. And if you see the complexes of such which is having the isotopic form nickel of 58 and 62, okay, nickel. So if you see this, so you can observe that the metal isotope shifts here in this, and the band assignments. So in this you can see that the nu of nickel, vibrations of nickel phosphine, okay, in such complexes is assigned at 270 per centimeter. This is what, okay, and uh, somewhat this is there. So initially it was placed at 470, 410 per centimeter, but it was observed at but this is not true, but this is what 270 per centimeter. So this complex is going to show the vibration here. So next, if you go for triphenyl phosphine PPH3, okay, so triphenyl phosphine PPH3, so this is the most common among the phosphine ligands, okay, and it is not so easy, however, to assign the frequency of metal to phosphine of phosphine complexes, okay, so because they are going to exhibit the number of ligand vibrations in the lower frequency region of 1550 to 155, lower frequency, okay, it's not this, a lower frequency. So this is what the problem is here. And by using the metal isotopes technique, okay, we'll see the graphical presentation also of that. Now if you see the tetrahedral, for example, so tetrahedral like NiPPH3 twice Cl2, NiPPH3 twice Cl2. If you see this tetrahedral NiPPH3 twice Cl2 complexes, so this was studied by Nokomoto, who is author of the textbook of this uh, spectroscopy of inorganic compounds. So for this tetrahedral, he says that it exhibits two vibrations of Ni phosphine, nickel phosphine. Okay, so two vibrations exhibits two vibrations, nickel to phosphine at 189 and 164 per centimeter, 189 and 164 per centimeter. This was a real agreement with the result of most of the papers, and very true value. So this is how he could from the IR spectra he could analyze this, and it was to the true to the previous researchers workers, so it tallied with this. So this is how the IR spectroscopy was very useful for knowing the different vibration by the help of different vibrational mode. So different structural isolation was very easy. Now if you see the complexes of type Ni PPH2 R twice Br2, okay, so Ni PPH2 R twice Br2, that is R stands for alkyl, allyl, anything you can shift it here. So diphenyl phosphine complex of nickel, so it exists in two forms. So either it may exist in tetrahedral and it may exist in square planar. Okay, so this is how. So this can be distinguished by how so with the help of IR. So if we go for the frequency of the NiBr here, okay, so and frequency of Ni phosphine, nickel phosphine Br. So this is going to help us now. Okay, so here of the planar complex, if you see of a planar complex, if you see this observed at 243 per centimeter. Okay, this observed at 243 per centimeter, that is planar complex. Okay, and if you see the vibrationals, these vibrations are for 195 to 182 for tetrahedral complexes. See, this is how is very important. Tetrahedral complex is this, and planar complex is going on 245 and 195, 182. So a little bit lower side, you can see that tetrahedral complex is we can see how it is going to be varied here. So even one graph I have taken here, so you can see the presentation of the nickel 67 and nickel 58 isotopic form of triethyl phosphine Cl2 and triethyl phosphine Br2. Okay, so these are two forms of 67 nickel and 58 nickel. So you can see here, so very sharp graphical presentation of these complexes here. So this is how the dotted line and see, so you can see dotted line of 62 here, so, and the thick line here of 62, okay, and dotted line of 58, 62, 62, and dotted line of 58. 8. Okay, so thick line you can see here, three almost they're coming at the same frequency here. So this is thick line of 62 and thin line is of 58, nickel 58. So almost you can see here 372, 396. Okay, small higher side is there, 403 here of 58 nickel, and see 372, 3 almost they are overlapping here like this, 329, 329. So this is very, so this is what been judgment with this nickel 58 versus nickel 62 with chloride as a halide here, so like this. And if you see now nickel 62 and 58 with respect to bromide halide. Okay, so bromide, so you can see here, so shift a little bit higher side is here, so here 372 is there, nickel 62. So you can see here nickel 62 thick line here, and if you see here nickel 58 for dotted line, so 374. So it's coming here, so you can see here 337, 327. Okay, so some difference is there here like this. So you can show some difference as the what do you say, the halides is been, so in chloride is there and bromide is in the second case. So like this this will is very much important, as well as this graph. If you see here the isotopic shift here. Okay, so higher frequency isotope shift here, and if you see the band assignment of these two, that is nickel 58 chloride and bromide here, and bromine chlorine. So you see here, so free vibration of the triethyl phosphine here, so it is 408 here, and this is a difference isomeric shift. Okay, so the delta nu is nothing but metal isotope shift here, so nickel 58 to nickel 62, the shift how much from here. So there is no shift here, but whereas in bromine you can see here, when the bromide is this isotope here, halide here used in this, so you can see here there is shift of 1.2. Okay, so there is shift of nickel 58, nickel 62 shift here, so this is a 1.2 here. So this is how the role of one halide in the, similarly you can see here for vibration is not seen here for the triethyl phosphine, but in the complex you can see that it is in 416 for the 403 here, and with shift here, isomeric shift of 6.7 between the two isotopic metal ions. But here you can see here it is 10.5, very high, so 6.7, 10.5. And this is because of the bonding frequency of the carbon phosphine and nickel. This is a tremendous change in the shift here difference between, because of the nickel halide, and again here less here because of the carbon phosphine vibrations, bonding vibrations. Okay, so here it is coming minus, shift is coming minus 0.1, but it is coming positive here, that is 1.1. Is it right? So this is how you can see that the change in the IR band and IR spectra will help us to denote the exact exact structural elucidation of the different complexes. Okay, different complexes of the isotopic nature also. Okay, and when the halide is being taken as a different mode. Okay, so this is how in tetrahedral complex as well as in square planar, so how we can distinguish. So this is how it's been shown by most of the researchers, and in fact is most complicated also. Okay, even in trans, the difference can be attributed to the strong trans influence of the phosphine ligands. Okay, absorption cis and trans, when you take the difference will be the more we can see in the transform, because of the most influence of the phosphine at the trans level. So this is what. Okay, and as such the investigators metal to phosphorus binding, so this also on the basis of electronic vibrational, they all have been detected number of complexes. Okay, based on the metal to phosphine bonding. Okay, so electronic vibrational NMR spectra, so most of them have taken from this, and with has studied regarding the degree of pi bonding in this. Okay, so they have studied regarding degree of pi bonding of metal to phosphine bond, metal to phosphine bond. Okay, so this also a study has been made by many of the scientists here, scientists, and they have given such observation. Okay, so they have given such observation. So this is how definitely and you can see that in most of the cases, most of the cases, the degree of pi bonding in square planar, degree of pi bonding in, okay, square planar, degree of pi bonding in square planar, like palladium 2, okay, and platinum 2, palladium 2, platinum 2 complexes was been also seen that by some research paper that the platinum phosphine pi bonding is much less. Platinum phosphine pi bonding is much less than the original predicted. So this is how, and it's very also difficult for to discuss the degree of pi bonding from this vibrational spectra alone, so we require other source also here. And this is how, and the metal to phosphine stretching frequency and the force constant is also been in some cases determined, okay, which says that it involves both type of sigma and pi bonding, so both type of sigma and pi bonding. So this is how the metal to phosphine what you say bonding complex is with the help of IR spectroscopy. So we can have, or we can have the structural elucidation, and this helps us in IR spectroscopy to know all these bonding sequences, okay, in the terms of the frequencies. Hope you understood this phosphine complexes. Okay, in the next class we'll go for arsine complexes. Okay, arsine complexes IR application. Okay, thank you.